What is the specific problem that the proposed method aims to solve in the context of in-context learning, ICL?
The specific problem that the proposed method aims to solve in the context of in-context learning, ICL, is the need for a more accurate and robust baseline for evaluating the performance of language models in few-shot tasks. The paper addresses the challenge of properly contextualizing the performance of models when dealing with small and idiosyncratic datasets that are used in few-shot evaluations. The proposed method introduces a maximum random baseline that takes into account the variance and validation set reuse, providing a more fair comparison for evaluating the effectiveness of prompts in few-shot tasks. By using this stronger random baseline, the paper aims to better distinguish between models that truly outperform random guessing and those that may be overfitting to the validation set. The method also helps in identifying prompts that may be overfitting and avoids unnecessary evaluations on test data, ultimately improving the reliability and accuracy of model evaluations in the ICL setting.
How does the proposed maximum random baseline method work? Illustrate step by step.
The proposed maximum random baseline method works by first considering the task of choosing the best prompt from a set of different prompts evaluated on a validation set. The method calculates the expected maximum performance among T-random classifiers, where each classifier guesses answers independently and uniformly at random. This calculation involves determining the number of correct guesses by the classifier with the highest performance, which is known as the T-TH order statistic or sample maximum. The method then utilizes the probability mass function of the binomial distribution to calculate the expected maximum accuracy out of T-random classifiers. This expected maximum random accuracy is influenced by the number of validation examples n, the probability of guessing a label correctly p, and the number of validation set evaluations t. By comparing the best prompt's accuracy to both the standard random baseline and the maximum random baseline, researchers can better contextualize in-context learning performance and identify prompts that may be overfitting. The maximum random baseline provides a more robust and fairer comparison by accounting for variance, validation set reuse, and the number of evaluated prompts, ultimately helping researchers make more informed decisions when selecting prompts for evaluation and avoiding unnecessary evaluations on test data.
What are the theoretical or practical benefits of using the maximum random baseline compared to the standard random baseline?
The theoretical and practical benefits of using the maximum random baseline compared to the standard random baseline are significant. The maximum random baseline provides a more robust and fair comparison when evaluating model performance in few-shot learning tasks. The maximum random baseline takes into account the variance and validation set reuse, offering a stronger and more accurate measure of performance compared to the standard random baseline. By considering the maximum performance among multiple random classifiers, the maximum random baseline sets a higher threshold for determining if a model's accuracy exceeds random chance. This helps in distinguishing true model performance from random fluctuations, especially in small datasets commonly used in few-shot tasks. Additionally, the maximum random baseline allows for a more precise and consistent evaluation metric across different datasets, taking into account factors like the number of classification options and evaluated prompts. It also provides a way to calculate p-values to quantify the fraction of random classifiers outperforming a prompt, aiding in better contextualizing model performance. Furthermore, the maximum random baseline can help in identifying prompts that may be overfitting and prevent unnecessary evaluations on test data, reducing the risk of overfitting to held-out test sets. Overall, the maximum random baseline offers a more reliable and informative baseline for evaluating model performance in few-shot learning scenarios, leading to more accurate assessments and better decision-making in model selection and deployment.
How were the experimental validation and testing conducted to evaluate the performance of the method?
The experimental validation and testing were conducted by partitioning each task into a validation set, 75%, and a test set, 25%. For a given model and task, the prompt with the highest validation accuracy out of t equals 200 evaluated prompts was selected. The validation accuracy of this prompt was then compared to both the standard random baseline and the maximum random baseline. The prompt was considered to outperform random on the held-out test set if its test accuracy was above the standard random baseline. This approach allowed for the prediction of whether test performance would exceed random guessing based on the validation accuracy. The comparison involved two classifiers, one predicting true when validation accuracy was above the standard random baseline, and the other predicting true when validation accuracy was above the maximum random baseline. By evaluating all predictions across multiple splits of datasets, it was determined that the maximum random baseline was a better predictor of whether test performance would exceed random guessing compared to the standard random baseline. The results were analyzed using metrics such as accuracy, AUROC, and AUPR to assess the performance of each baseline in predicting test set accuracy.
What were the key results achieved with the maximum random baseline method in the study?
The key results achieved with the maximum random baseline method in the study include 1. The expected maximum random baseline provides a more stringent threshold for evaluating model performance compared to the standard random baseline, especially for small datasets used in context learning (ICL) tasks. 2. By using a family of parametric distributions to represent random performance, the maximum random baseline allows for a comparable performance metric across multiple datasets, considering factors like the number of classification options and evaluated prompts. 3. The maximum random baseline helps in identifying prompts that may be overfitting and avoids unnecessary evaluations on test data, thus reducing the risk of overfitting to held-out test sets. 4. The maximum random baseline can be easily calculated as a drop in replacement for the standard random baseline, providing a more accurate assessment of model performance in ICL tasks. 5. The study found that the maximum random baseline recontextualizes in-context learning performance, leading to a better understanding of the difficulty of different few-shot tasks. 6. Results showed that the maximum random baseline predicted held-out accuracy more effectively than the standard random baseline, reducing the number of false positives and providing higher precision in predicting test performance above random chance. 7. The maximum random baseline identified model dataset pairs with weak performance, helping researchers gain more confidence when maximum validation accuracies exceed random performance. 8. The method of comparing maximum validation accuracy to the maximum random baseline was more indicative of whether held-out accuracy exceeded random chance compared to the standard random baseline. 9. The maximum random baseline disagreed with the standard random baseline in a significant percentage of experiments, highlighting the importance of using a more robust baseline for evaluating model performance in ICL tasks. 10. Overall, the maximum random baseline method provided a more rigorous and reliable framework for evaluating model performance in few-shot tasks, offering insights into the variability and challenges of different datasets and prompting strategies.
What are the limitations or drawbacks of using the maximum random baseline method?
The limitations or drawbacks of using the maximum random baseline method include the fact that it may not be a perfect predictor of model performance on truly held-out test sets. While the maximum random baseline can provide a better indicator of whether test performance will exceed random guessing compared to the standard random baseline, it is not foolproof due to the possibility of a low-quality prompt achieving high validation accuracy by random chance. Additionally, the maximum random baseline may lead to fewer false positives compared to the standard random baseline, but it can still result in incorrect predictions about test performance. Furthermore, The maximum random baseline method relies on assumptions about the distribution of random classifiers and the order statistics of the binomial distribution, which may not always accurately capture the complexity of model performance in real-world scenarios. Lastly, the effectiveness of the maximum random baseline method may vary depending on the experimental design parameters, such as the number of validation examples, the number of evaluated prompts, and the number of classification options, which could limit its generalizability across different settings.